Hello everyone, welcome back to the course on architectural design of ICs. So, in the last class we have seen that one's complement circuit, controlled one's complement circuit, and we have discussed that two's complement. We find out how we find out the two's complement circuit. That means we find out the one's complement of the circuit, then we find out one's complement of the number first, then we add 1 to that becomes 2's complement. Okay. So, that means now what from that particular point or from that particular perspective we can see that one circuit that can be act as one's complement as well as 2's complement. So, at that time how we can, that means draw a circuit or how we can design a circuit which can gives me both the things at a time. That means that the circuit will remain same, only I have to put some additional control logic to it, so that I can get the in one particular circuit I can get one's complement as well as two's complement. Okay. So, that we will see in today's lecture. So, if you follow this two's complement circuit, so enable and that means complement, this is 2 control signal. Whenever this is 0 and cross, at that time it will remain unchanged. When enable equals to 1, so at that time, that means E signal is 1, at that time I will get 2's complement, or whenever the C signal is 1, so at that time I have to get it 1's complement. That means now I am having 2 control signal which is E and C. So, based on that, if E is 1, okay, if E is 1, so at that time I will get 2's complement, if C is 1, so at that time I will get 1's complement circuit. So, what is that? That means hints here, as I discussed that what that means I have to do this one's complement, and then if we add it by 1, then it will become this 2's complement circuit. So, in one's complement circuit, what we do? We use XOR gate. Okay. So, in whenever and if you see this incrementer by 1, so at that particular case also we use the series of XOR gate. Okay. That means now can I conclude, or can I, that means make the expression in such a way so that I can make it common. That means I can reuse those XOR gate for one's complement as well as this 2's complement circuit. So, can I do that? So, that we will see in this particular lecture. Okay. So, for that, and what is the hints here? That is, keep the first one from the right and then invert all other leading bit. Okay. So, that means the corresponding equation for that will be, whenever we are adding 1, that means I have to generate the carry, right. So, generate the carry means how we can generate the carry. So, for carry I can calculate by using this particular equation, which is A I plus C I minus 1, which is the previous output, previous carry output, that means previous stage carry output, that will be added with, that will be OR with the corresponding positions of the inputs, and that you will get the corresponding carry out, okay, for that particular stage. And for the A out, that means which is nothing but that 2's complement or this one's complement circuit. So, that you will get by this A I XOR with E of C I minus 1. That means, the previous carry that is added with the enable signal, and that is XOR with the corresponding input bits. Okay. So, if I just want to draw this particular equation, that means if I just want to draw 4 bit this one's complement come 2's complement circuit. So, at that time how it will look like, that we will see, that architecture we will see in okay now. So, what was the equations? So, if I just write the equation something like this. So, C I is A I plus C I minus 1, okay. And what is this A out? That is A I, this is A I XOR with E C I minus 1. So, these two equation basically is followed to calculate or to compute the corresponding architecture for that. So, here actually I means this is for I bit. So, if I consider 4 bits, so at that time how the architecture will look like. So, in the initial case, and if I just go back, in the initial case this C I minus 1, that is equals to 0. That means, for the first stage, as there is no carry, so that is been the carry in as considered as 0. Okay. So, now for this first case, so that means what I need, I am having 4 XOR gate for the, from here I will get A out 3, this is A out 2, this is A out 1, this is A out 0. Okay. Now, this is A 3, this is A 2, this is A 1, this is A 0, this is A 3, A 2, A 1 and A 0. Okay. So, the next, if you just go back, A out is dependent on what? A I XOR with E of C I minus 1. Okay. So, that means to calculate these particular things, I need one AND gate in each of these corresponding XOR gate input. So, that means here what I need AND gate, here I need one AND gate, here I need one AND gate, and here I need one AND gate, where each of the input of this AND gate, that is fixed to E. Okay. Then what is the other input? The other input is the carry out of the previous stage. So, the carry out, how we can that means calculate? The carry out I can calculate by using A I XOR with C I minus 1. That means, for that what I require? I require OR gate, as you see here, that means this is the OR operation, sorry, this is OR operation A I OR with C I minus 1. So, that means now this is this, and actually if I start from here, so that means this will be the another case, here also I need one OR gate. Okay. So, one of the input is this, as there is no, that means previous of this input. So, that is why OR gate is not needed for this last stage, okay. But the rest of the case it is required. So, then what will be the other input is this one, for this one, and for this what will be the case, that is C I minus 1. Okay. So, now if you see, that means I have drawn I have calculated the carry out for the previous carry out, I will get from this, and then I will end with E, and I will get this in this fashion. So, now if I just want to verify this particular circuit, that whether that is that means what was my target, if E equals to 1. So, at that time it will be act as a 2's complement. If E equals to 0, so at that time it will act as a 1's complement circuit, 0 and C equals to 1. So, at that time it will act as a 1's complement circuit. Okay. So, is it doing the same thing? So, initially you check E equals to, that means if E equals to 1. So, at that time each of this particular bit is, this is 1. Okay. 1 means now this will depend on the corresponding carry of this. Okay. So, that means if one incremental circuit, at that time what will happen? This is nothing but the incremental circuit. Okay. So, this incremental circuit means what? So, at that time what will happen? I will just add it by 1 here. So, whenever I am adding this, that means E is 1. So, then the AND gate output will depend on what? This particular input. So, this will, the output of AND gate will be this one. Okay. So, as I am following, or as I am doing this, putting this carry in this particular chain towards the MSB. So, at that time this carry will be propagated, and then that will be XOR with the corresponding bit position of A3, A2, A1 and A0, and you will get the A out, that means the corresponding 2's complement circuit. Okay. So, this is the controlled 2's complement circuit. Okay. So, now if I just want to, that means make this as, if I want to make it, that means work that as in 1's complement circuit. So, at that time what I need? I need that this particular position should be 1. Okay. So, this particular position to be 1. So, then what I need to do? For that, what I need to do? To calculate that, I have to do, that means if this is 0, then this will be what? 0. So, but I need, for this inversion, I need this as 1. So, that means now at that time I have to make it the bar of that. Okay. So, that means if I put it as this E bar at that time, so then it will be 1, and there I need to change the corresponding this value to, so that it does not affect the corresponding. If this bit is 1, that means at the time it will be dependent on that, and then I can get the corresponding value for this. Okay. So, this is for controlled, basically 1's complement circuit. Whenever I have to implement, at that time I need to change something so that it can work as a 1's complement, but this is controlled 2's complement circuit, by which we can get, that means this is for 4 bit, for n bit this will just continue, that means this particular position will continue, and then at the final stage also we will get something, these values here AND gate, and that will be OR with the carry in will be generated from the OR gate, and then that will be ANDed with enable signal, and you can get the corresponding AND bit sum output, sorry, this 2's complement value output. Okay. So, this is for control 2's complement circuit implementation. Okay. So, then next we will see another example of, let us go back to the slide. Okay. So, then next what we will do, we have to find out sum of n natural numbers. Suppose this is my job to do, I have to find out sum of n natural numbers. So, that means sum equals to 1 plus 2 plus 3 plus up to dot 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 up to n. So, n I can specify that n value to 100, n value to 150, 200, 1000, any value I can set. So, how I can implement this particular circuit? So, first you consider, that means S equals to 1 plus 2 plus 3 plus dot 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 plus to n I have to. So, if I just, that means this is means what? 1 that is added with 2, then that is added with 3, then that is added with 4, then that is added with 5. If I consider, let us say n equals to 8, 5, 6, then 7, then 8. Okay. So, that means these 8 numbers I have to add. So, what we can do? We can use the adder something like this, where I can put 1, 2, 3, 4, 5, 6, 7, 8. Then this again I have to add, then this to this. Okay. So, that means here you see how many numbers of adder I require? Total 7. So, this is that means the case, or this is for any n bit number of addition in this particular fashion, I need n minus 1 number of adder. Okay. So, then there is another implementation style for this, and what is there? That means the corresponding delay for that, that means as there are 3 levels of adders. So, the delay becomes 3 t adder delay, as there are 3 level of adders. So, that means for this particular implementation, I need n minus 1 number of adders and the delay with 3 adder delay. Okay. So, if each of these bit, if I consider that as 4 bit or 8 bit, so at that time I require, for if this each of this bit is like, if I consider that as 4 bit or 8 bit, 4 bit if I consider, then at that time what how many full adder cell I require? 7 into 4, that is 28 number of full adder cell I require. So, is there any other that means different that methodology or different techniques to implement the same thing? Yes, there are, or there is. Okay. So, this expression if I can write in another form, where that is S equals to n into n plus 1 by 2. This is the expression of summation of n natural number. So, if I just want to add this, or sorry, if I just want to implement this particular circuit, so at that time what I require? I require one incremental circuit here, and then I require one multiplier over here, and divide by 2 means I will just discard the LSB, that is hard shift. If I discard the LSB, that will be divided by 2. So, for divide by 2 I do not need any extra hardware, but here the hardware wise or area wise what I require is one multiplier and one incremental circuit. And what is the delay? delay is 1 multiplier plus 1 incrementer. Okay. So, that means this is another, that means implementation style by which I can make the corresponding, I can implement the corresponding expression for n summation of n natural numbers. So, in these two particular case, in this case, if this considered as case 2 and the previous, this is case 1. Okay. So, what is this 2 case? Here what I am doing? I am calculating the values simultaneously or parallelly. Okay. So, that means I am putting all these values, what I am doing? I am putting all these values parallelly to this particular circuit, and then I am getting the corresponding output. If I consider this as this, that means with register we put at this particular level and register we put at this output level. So, this is the critical path, which is nothing but this T delay, 3 T that means added delay, and this is, that means from this particular path to this, that I can compute within 1 clock cycle. Okay. So, the next thing also the same thing, here also I can implement this particular function in one particular case. Then actually where I need to, if you just see 1 plus 2 plus 3 up to dot dot n, using this fashion I can do. And here also this 1 star that means n dot n plus 1 by 2 also I can implement. Where I will use this particular circuit? Where I will use this particular circuit, though actually the delay for this particular circuit is more than the previous case, but this style is also I can use somewhere. Where I can use? When the n value is very large, okay, that means if the n value in previous case I have set to 8. If the n value is, let us say that means 512. So, at that time designing this particular architecture will become too much of complex. That means, at this particular stage I need 256 adder, then at this particular case I need 128 adder, then I need 64 adder, then I need 32 adder, then I need 16 adder, something like this I require. So many levels, and I require this kind of structure, tree structure of the adders. So, describing using HDL or any other language, that will become too much complicated whenever I am following this particular method. So, at that time, instead of that, when the n value is more, at that time what will happen? If I specify this, only here what I need? If I just draw this, what I require? I need one, I need to put this as n, this is incremental circuit, okay. Then that will come over here. So, this is incremental circuit which is multiplied with this. So, here I will get the corresponding sum. So, whenever this n value is 512, so I do not need to, that means change here, only the thing is that I need to load the value of n only once. I do not need to for 512 or 1024 or 2048, I do not need to describe any other, that means adder, which I have to do in the previous case. So, for those type of application or for those type of things where circuit implementation, I will follow this kind of architecture or this kind of circuit implementation. Okay. So, then is there any other technique or other method by which I can implement the same function? Yes, there is. Okay. So, what is that? That is the iterative method. Okay. So, that means iterative method, it means using only one adder, I will run that particular things, that means this particular, that means I'll in each of the stage I will add, I will store it somewhere, and then again I will add to the next that storing value, that will again I will add with the next value. So, something like this, then whatever n value I have loaded, up to those values, unless and until it is reaching to those particular values, it will try to, in each of the clock cycle, it will try to add and then accumulate, add and then accumulate, add and then accumulate. So, whenever we will get the final result, so at that time it will freeze and it will go to the corresponding output. So, that means compute this iteratively, the algorithm is something like this. The input is n. Okay. So, that means the here you see this input is basically n, initial, that means the sum is 0, and then for I equals to 1 to n, s will be, sum will be that means modified with previous sum plus whatever value is there, that is the I. And whenever this job is finished, then change the corresponding I value to the next, and when all this is finished, then output you just assign to the, that means the s value that will be assigned to the corresponding output. So, from this particular algorithm, so if I just want to map this particular algorithm into the architecture, at that time what do I require? If I just follow, or if I just closely, that means see, I am having 3 variables. What are those? I am having, I needing this n over here, then I need s, and then I need I. So, that means I need 3 variables for computing this particular that means this logic or this particular algorithm. If I want to implement, then I need 3 variables, and then for this particular I need one adder, and rest of the things we will just, whenever we will draw the corresponding architecture, at that time we will see that. Okay. So, if I just want to map it to the architecture for this particular algorithm. So, what is that? That is input is n, initially s is 0, then for I equals to 1 to n, s equals to s plus I, then next I, and put the output as s. So, this is my algorithm for computing the sum of n natural numbers. So, that means what I said, that I am having 3 input variables, sorry, not input variables, I need 3 registers or 3, that means for n, as there are 3 variables n, s and I. So, I need 3 register n for n, s and I. So, initially what I will do? I will put that like this. Okay. So, this is s, this is n, and this is I. I is what? I is basically is a up counter, which is basically counting from 1 to n. So, what I require initially, I need the control signal for each of these registers. So, initially S is what? S is 0. So, this will be clear. Initially this registers will be clear. For n, what I require? It will be load. That means, initially I need to load the values of n to this particular register, and this for I whenever this is started, this has to start with 1. So, that means, then this will be what? This will be initialize the counter with values of 1. Okay. So, then next what I have to do? I have to do this S plus I. So, that means, I need one adder circuit, and then output of that is again connected with S. Okay. Then S, that means S is basically connected to this, and this value is again connected to this. That means, in one cycle the previous S is coming here, that is added with I, and then again it is going back to, that means the corresponding output that has go back to the sum registers. Okay. So, from this is the external bus. So, this will load from the external bus only. I can load the values of n, and again I need to, that means deliver whenever this job is finished. So, at that time I need to deliver the output to the external. So, what I require is that I require one buffer over here. Okay. So, just want to I need one buffer over here. Okay. When this total job is finished, so at that time this buffer will produce the corresponding this S value will go out via through this external bus. Okay. So, what will be the condition for this will be enabled, so that this S value can go out to the external bus, and what is this is a loop running, right. So, what is the terminating condition? So, terminating condition is that means it has to reach to the n value. So, that means I need one equals to comparator whenever this I equals to n. So, at that time what will happen? It will try to stop. Okay. So, that means whenever this value is equals to n, so at that time this will come and this will again start from 1. Okay. And this particular signal is the terminating condition. So, this if I just say that is or that means output enabled. So, this signal will again be connected with this particular signal. That means, whenever this signal is 1, so this will be enabled and S will be at that time it will go to the external bus. So, this is the corresponding algorithm was that for finding out the n natural numbers. The corresponding iterative circuit for calculating n natural number is that. So, now if I that means have to if I put that n equals to 512. So, in each cycle it will this circuit will basically run and it will try to compute 1 plus 2, then 3, then 4, something like this. That means, as this count value is basically increasing, initially it is 1, then next cycle it is 2, then 3, then 4, and where I am doing the addition. So, initially it was 0 added with 1. So, 1 is stored here, then in the next it is 2. So, 1 is coming from here. So, 1 plus 2, then this is 3. So, 1 plus 2 is already stored here. So, it comes with 1 plus 2 plus 3, then next it is 4. So, 1 plus 2 plus 3 that is stored here. So, 1 plus 2 plus 3 comes here in the next cycle. So, 1 plus 2 plus 3 plus 4 that again comes with this. So, in this fashion or in this manner this basically runs, and how many times it will run, that means up to this 511 clock cycle it will run. Okay. So, that means this 512 clock cycle it will, this particular circuit will run, and in the 512 clock cycles I will get the output at the external stage, that means external bus, if I select this n input as 512. So, then if you see here area wise, that means what is the benefit of this circuit? Area wise what I require? Only I require 3 resistors and 1 adder and 1 comparator. So, 512 I need 5 1 11 for case 1, and for case 2 that is fixed, 1 multiplier and 1 incrementer, but here what I require? Only 1 adder and 1 comparator, and resistors are like there also you require resistors. So, if I say that here I require 3 resistors. And delay wise what is the maximum delay? So, delay wise is that this resistors delay or this and this adder delay, that is the maximum delay which I can get from this particular circuit. So, delay wise also it is very much faster than this case 1 and case 2. But where actually whenever we are gaining something, at that time we have to lose somewhere. So, where is the lose point? I am losing here the time, that means for total computation time of the corresponding circuit. So, there within 1 clock cycle I can finish the job, but here for 512 number of samples if I want to add, then up to 511 clock cycle I have to wait. After 511 clock cycle, then only I will get the corresponding output. Okay. So, in the next class or in the next few classes we will see. So, this is the corresponding algorithmic the architectural implementation of this particular algorithm. Can I optimize this particular circuit? Can I do that? If I can do that, then how or what is the approach where I will look into, so that I can find out, okay, this is the point where I can look into and I can optimize this circuit. So, that we will see in the next classes. Thank you for today's class.